Right, so it's recording. So just so that you know that it is now recording, you'll see at the top left, it says the meeting's being recorded. So let's have a look at exercise 18. Okay. So exercise 18 says we're dealing with Upper Meridian Passage for selected stars. Okay, now just a bit of background as to what's happening here. So you'll see the question, we're going to have a look today at question number 2. So we're going to do question number 2. And you note that it says they list the selected stars that would be suitable. So the first thing when we're dealing with stars, so when we're at Sun and Venus, any calculation on that, you exactly know what body it is you're dealing with. But with the stars, you're looking at tomorrow morning, isn't it? Because the whole point of this question, these kind of questions, is that you're planning for a later time. So you're basically looking, in this case, we're saying during the morning twilight on the 22nd of October. So you would be on the 21st of October, let's say the evening, planning ahead for the next morning, isn't it? Now you don't know ahead of time exactly which stars are going to be visible at that time and which stars will be at Upper Meridian Passage. So that is the point of this question. So in this case, we're saying, look, we don't know which stars are going to be at Upper Meridian Passage, so we need to get a specific time or a range of time, let's say between 4 o'clock and 4:30 tomorrow morning, and we need to then check which stars will be at Upper Meridian Passage during that time, because that star can then be taken as a point of calculation at Meridian Passage. So if we look at this question, it says list the selected stars that would be suitable for observation at Upper Meridian Passage. Note that it will always be upper, right? It's only the Sun that could be Lower Meridian Passage, or at least in the syllabus that we're covering, it will only be the Sun. So selected stars suitable for Upper Meridian Passage during the morning of the 22nd of October 1979. Now again, I know that not everybody has the 1979 almanac, so in the exercise today, we can use the 2020 almanac. If you have the 79, it's fine, you can carry on using it, but I'll use the 2020 in the example. And you will note that the change isn't that significant. I mean, as we've discussed before, if you're looking at throughout the years, the movement of the stars, because they're so far away, is not that great. So there's very little change in the answers. In any case, so 22 October, if the observer was in the following position: 32 degrees 40 minutes south and 96:36 east. So everyone can just write that down if you haven't done that yet. Right. So what we need to do, it says here, we need to predict the GMT and the zone time and the sextant altitude. And this, of course, HS would be a predicted sextant altitude. And also the azimuth for each selected star. So that means there could be more than one. We could have one, we could have two, we could have three. In this case, we'll have two. Okay. So we need to get the GMT, the zone time, the predicted sextant altitude, the azimuth for each selected star in the list. And then it says you've got an index error 1.8 off the arc, and the height of I is 24 meters. All right, so if we open up the setup here, so I've already set all of this up. I'll explain everything as we go along. The first thing we got to do is find the approximate time, like we did with the question normally. So we're going to find the approximate time during which we can observe stars. Okay, now you might remember from S1 and S2 that the best times to observe stars was during twilight. And I'm not going to go into all the details of nautical and civil twilight and the difference between the two and all of that. That's not really important at this stage. You're welcome to go and read up on that if you want. But I'm not going to go into all of that detail now. What you need to know is that we're dealing with nautical twilight, NT, and civil twilight, CT, and that's of course in the morning, so AM. So morning twilight, nautical and civil. And this is going to give us an indication of the times during which we will be observing the stars. So twilight is basically the best time to observe stars because it's light enough that you can see the horizon, but still dark enough that you can see the stars. That's basically what, in simple words, that's basically what twilight is all about. Because you want to, so it's before sunrise, obviously in the morning, which means there's already some light that illuminates the horizon, so you can still use the horizon for a sextant sight. And of course, it's dark enough that the stars are still visible. Okay, now what we need to do is we need to go into the almanac and we need to now go and find the time for these twilights on this date. Okay, so let's have a look. We go into the almanac on the 22nd of October. Guys, if you're not sure what I'm doing, just let me know, eh? Stop me so that I can explain it again. 27 October, 24. Okay, 21 to 23 October. Of course, this is 2020. Now, if you look at your tables, on the first page, of course, this would be the page on the left. You've got Aries and Venus and planets and the stars. And then the next page on the right, we have the sun, the moon, and then your twilight sunset times. So if you look at this, at these times, let's say, just look at the top one here. They follow chronologically, left to right. Okay, so in the morning, on any one of these days, in the morning, the first thing that's going to happen at 5:27 at this latitude, at 5:27 is going to be nautical twilight. Then the next thing at 6:46 will be civil twilight. And then at 08:02 will be sunrise. So it's first nautical twilight, then civil twilight, then sunrise in the morning. Then in the evening, it swaps, it goes the other way around. So then you'll have sunset at 3 in the afternoon. Then you'll have at 16:41 there'll be civil twilight, and at 17:59 you'll have nautical twilight. So this would be in the evening. Okay, so currently we're interested in the morning. So what we got to do is we got to go and find the time for nautical twilight and the time for civil twilight. Because during this time here, between these two, that is the best time for observing stars. Okay, and taking star sights. But now this is at 72 degrees north. We're not at 72 degrees north. We're south. We're 3240 south. So we need to go all the way down. You'll see over here you have 30 south and 35 south. So the values that we're interested in is over here. So we're at 32, so we're in between 30 and 35. So at 30 degrees, so the time for nautical twilight, the first one that we're interested in, the time for nautical twilight at 30 degrees south is 04:20. And then the time, same time at 35 is 04:11. So we have 04:20, 04:50 for civil. So for nautical twilight, it's 4:20. For civil twilight, it's 04:50. And this is at 30 degrees south. And then the next one, and you can write this down, the next one is at 35 degrees south, and that's at 04:11 and 04:42. So just write these values down. Right. Now, if we go back to our sheet here. Right, so tabulated time. Okay, so it's obviously an LMT. So remember, we said that these times that are given in the almanac with regards to meridian passages, those times are all LMT, local mean or local meridian time. So it's basically the exact time for that specific thing. Like in this case, it's twilight at your latitude and at your exact longitude. So that means that needs to be corrected again. You need to apply a longitude correction to get it to GMT, and that's exactly what we're going to do here. Okay, so it's an LMT, and it's at 30 degrees south. So over here we had 04:20, and over here we had 04:50. Everyone happy with that?
Yes, sir.
Right. Okay. So we had 4:20 and 4:50. This was at 30 degrees south. Okay, so I think what I'm going to do over here is just put that in there as well. And then we had below this, we had 04:11, and over here we had 04:42, isn't it? And this was at 30 degrees south. And this was at 35 degrees south. Correct? I'm just going to move this out of the way for now. So we had 30 degrees south, and those are the values given. And we had 35 degrees south, and that's the value given there. But now we are somewhere in the center. So we're over here at 32:40 south. Right. Now that means that we will need to interpolate for this value. Right, so we need to interpolate for X and Y in this case. Right, so if you thought that you're never going to see interpolation again, I've got bad news for you. But luckily, it's not really a difficult thing, eh? If you can't remember how to do interpolation, guys, I would suggest that you go and sit with this. If you're struggling with this, I suggest you go and sit with these kind of questions and go and play around with them a bit. It's not that difficult. You can set anything like this up for yourself. You can make this value anything, you can make that value anything, and you can practice interpolation as much as you like, okay? But it's important that you understand this principle because you're going to use it again and again and again moving forward. Now, in this case, we have a shift of 5 degrees, right? So we have 02 degrees, 40 minutes. Actually, what we could just do is this 2.66666. It's basically 2 2/3 degrees, isn't it? Over 5 degrees. This is our fraction. Do you agree? So if you take 2 degrees 40 out of a total 5, it's going to give you this fraction. And that fraction is equal to 0.53333, like this. Do you guys agree?
Yes, sir. It's right.
Okay, you're happy, right? Is anyone unclear of how I got to this? Remember, guys, you need to speak up, otherwise I don't know. Okay, so that's a fraction, right? Now, the total change here for the 5 degrees, the total change there is 9 minutes. And the total change here is 8 minutes. Okay, that's a total shift, 9 and 8. Now, if you take these two values and you multiply it by the fraction, then that's going to give you an indication of the shift from the starting position down to x and the starting position down to y, isn't it? So you take your fraction, multiply it by 9, you're going to get 4.8. We can round that up to 5, because remember, everything here is to the nearest minute. So it's fine, you can round that up to 5. And then in this case, you'll get 4. So this one's 4.26, and that you can round down to 4. So this means that the shift from 420 down to x is 5. The shift from 420 down to x is 5. Obviously, this is decreasing because it's going down towards 11. So in this case, then it'll be 420 minus 5, and that's going to give you 415. Everyone happy with that? Shall I say, is anyone unhappy with that? All right, so that gives you 415. This one is 4 minutes. It's exactly the same thing. We're going down, we're subtracting. So this one becomes 0446. So this basically means that the corrected LMT, right? So the corrected LMT, so we started with the tabulated LMT at 30 degrees south. Now the corrected LMT at our latitude, which is 3240, and you will see that I've got the same fraction that I had done here. So the corrected LMT at our latitude becomes 415 and 0446. Okay, so that's basically what we have over here. So you don't need to write all of this. You can obviously keep this somewhere for your calculation, but in the table, you don't need to put all of that in. You can just put the values in there, that's fine. Is there any questions on this? Or any unclarity on what we did here?
Please, the interpolation is not clear, please.
Sorry?
The interpolation.
What about it?
Okay, can you please run over it again? That's okay.
Okay, you're very unclear. I take it you want me to explain it again, is that right?
That's correct.
Okay, right, so I'm going to go through it one more time, but I can't spend too much time on this. So because this is something that you should know, like I said, I suggest you go and practice this if you're not familiar, but I'll run through this one more time. So we started at 30 degrees south. That was in the almanac, that was given. And then we had 35 degrees south in the almanac, that was given. So there was a 5-degree change. So from there to there was 5 degrees total change. And the change in minutes there was -9 total. So for 5 degrees, for a total of 5 degrees, we had a change in -9 minutes and a change of -8 minutes. Okay, so for 5 degrees, changes by 9 and changes by 8. Okay, now in our case, we don't have this, we don't not interested in the full 5 degree per se. We are interested in 3240. The values we want is somewhere in between these two. So what we need to do is we need to say either from the top down or from the bottom up. It really doesn't matter. In our case, we go from the top down. We need to say there's a fraction. So if 2 degrees 40 minutes out of 5. Okay, so we're going from 420 downwards by 2 degrees 40 minutes out of a maximum 5. So that 2 degrees 40 minutes, 2.666 degrees over 5 is going to give you a fraction. Okay, so we've gone down by 0.53 out of 1, isn't it? So it's a fraction of the maximum value. And that fraction is 0.5. So we simply take 2 degrees 40 minutes, you take this value here and you divide it by the total. It's going to give you 0.53. So we say we know that the fraction is 0.53. So that same fraction needs to be applied to the change in time. And the change in time is a total of 9. We multiply that by 0.53, you're going to get 5. Rounded up. Then you do the same on the right here. You take the 8 minutes shift. You multiply that by 0.53, you're going to get 4 minutes, and that's obviously been rounded down. So the total change then, at our given latitude, the total change, instead of the maximum 9, it's only going to be 5, because that's been calculated by the fraction, and instead of the maximum 8 on this side, it's only going to be 4. So from 420, we go down by 5, we get 415. And from 450, we go down by 4, we get 446. All right. So that corrects this LMT. Okay, now from here, everything else going down here is straightforward. But you can see how crucial this step is, because if you miss this and if you make a mistake there, you're going to have quite a problem, because that means that everything else is going to be wrong. So this is a very important step. That's why I said, people, if you're not sure with this interpolation, you need to go and practice this. Okay, if you're a little rusty. Right, okay, so we get 415 and 446. That is the corrected local mean time for nautical twilight and civil twilight. But now we know that we're not really interested in LMT. LMT is at a specific meridian. We're interested in GMT. The question asks for GMT and for zone time, isn't it? So what we need to do is we need to take our longitude, 96 degrees, 36 minutes. We need to convert that to time, and then we need to apply that to our LMT. So if you take 96 degrees, 36 minutes, and you divide it by 15, what do you get?
Six hours, 26 minutes.
6 hours, 26 minutes. Like that.
Yes.
Okay, so you get 6 hours, 26 minutes. Now our longitude is east. So we are east of Greenwich at 4:15. We're going back towards Greenwich. So that means we need to subtract. And when you subtract 6:26 from 4:15 in the morning, that means you're going back into the previous day. So you go back into the previous day and you subtract that, you're going to get for nautical twilight, you're going to get 21:49. And for civil twilight, you're going to get 22:20. And that'll be on the evening of the 21st. Everyone happy with that?
Yes.
All right.
Yes, sir.
Okay. So this gives us an approximate GMT. Now from there, we need to apply a zone difference. A zone difference in this case at that longitude, the zone would be zone Foxtrot, zone F, which means we're going to add again, going back east. We're adding 6 hours. And that will, of course, take us back to the 22nd again. And it's going to give you 0349 and 0420. Right, so now we know that for the next morning, so in the morning of the 22nd, on board, we are going to look, because the ship is obviously keeping this time, the ship's keeping zone time. You could put in your ST for ship time or local time, zone time, whatever. In this case, it's zone, it's fine. So this will be the ship's time. So the following morning, between 3:49 and 0420. So 0349 will be nautical twilight, 0420 will be civil twilight. And between those two times, so that's a 31-minute interval. And that 31-minute interval will be the best time for star sights. Okay, so we've now calculated the time ahead. So we know that that's going to be the best time for star sights. Now, that means that if we want to look now for a star, we want to find a star that is at Upper Meridian Passage, then it needs to be at Upper Meridian Passage between these times. So the star must be at Upper Meridian Passage between 3:49 and 0420. So in that 31-minute interval. Right. Now, when we are looking on the side here at the angles, working with the hour angles, you'll see that I've added another column. So in the previous exercises for the Sun and Venus, we only had the one column running down. So in this case, we're going to do everything double. So because we're using 2 times here, so working with 2 different times, that means we're going to use 2 different columns. Okay, so we're going to do one for AM, nautical twilight, and we'll do one for AM, civil twilight. So you're adding a second column here because of that second column. All right, but other than that, this thing is going to work very similar. But now you will see, instead of working down to an HA, so instead of working down to an HA, we are including the HA in the calculation, and we're working all the way down to an SHA. What's an SHA again? Anybody?
Finish.
Sorry?
Polar angle.
Polar angle, right? So it's a sidereal hour angle. That's what it stands for, and you're quite right. It's a polar angle, and it indicates the difference or the angle between, in common terms, basically the angle between Aries and whatever star it is that you are looking for. So between Aries and any other star. And the reason why we use this is because the Aries is the only one that is tabulated in the almanac. That's tabulated at an hourly interval, whereas your other stars, they are not. They just give it an SHA. Okay, so what we are looking for, so we're going to say, fine, we need to have it, so at these times, we're going to run this down to an SHA, and we're going to run this one down to an SHA. And that's basically going to tell us these 2 SHAs that we're going to calculate. That's going to give us an indication to say, okay, any star between this SHA and this SHA, will be at Upper Meridian Passage during that time. So that's basically what we're doing. We're saying, okay, we know it must be at this time. So this time we run that time down, starting at Upper Meridian Passage, because obviously this is what we are looking for. We're going to work on what is the SHA for a star at Upper Meridian Passage at this time. That's in this column. And then in this column, we're going to say what is the SHA for a star at Upper Meridian Passage during or at that time. Does that make sense? So this one will be for this time, this one will be for this time. That's going to give us an SHA and an SHA there, and an SHA there. And that means that any SHA that is tabulated, or any star, and then we'll go back to the almanac, any star that has an SHA between year and year, any star that falls in there, they will then be at Upper Meridian Passage during the time that we are looking for. Okay, so that's the purpose of this part here. So to start all of this off, we'll do the same thing that we've been doing up until now. We're going to start at 360. So the LHA for a star at Upper Meridian Passage will be 360. And from that, we will subtract an east longitude and it's going to get you the GHA for the star at Upper Meridian Passage. Okay, so we have the GHA for the star. And we ultimately want to find SHA for the star, so that means we need to subtract the GHA for Aries, because you'll remember somewhere in S1 you had something like this. You had something that looked like this. LHA star was equal to GHA Aries plus SHA star plus minus longitude, something like that. And that's what we do in that table as well when we do a Marx interlaid, and we basically do this, isn't it? So we're just doing the same thing here. We're just taking this, if you look at this as a formula, we're saying, okay, but now what we're looking for is this one only, SHA star. So that means it's going to be LHA minus, or plus or minus longitude, minus GHA Aries, and that's going to get us to this. And that's exactly what we're doing here. So apply the longitude first, then we're subtracting GHA Aries. That's going to get us SHA star. Okay. Now, this is very important, guys. Up until now, you'll see again I highlighted it in yellow because we're looking at this date and time. So again, this needs to correspond. But for the two columns, you need to treat these two columns, even though some of these values are the same, like in this case, you still need to treat them as individual columns. Okay, so that means you need to look for the left-hand column. You need to specifically look at the time on the left. And for the right-hand column, you need to specifically look at the time on the right. And you will see in this case that the left-hand one is at 2100, 2149. And the right-hand one is at 2200. So that means you're going to enter the almanac first at 2100 for this one, and then at 2200 for this one. Does that make sense?
Yes, sir.
Right. So please be careful with that. In some cases, right, in some cases you're going to have a calculation, and this could be 2114 and this could be 2150. That's fine. Then you've got the same one. But I'm just saying be careful of that, because you need to be sure when you go into the almanac that you're going in at the right time. So you must enter this, the left one for AMNT, you must enter at 2100 in this case. And for AMCT in this case, you must enter at 2200. Okay. The date, of course, will still be the 21st, so that rule's still the same. Must be the date at GMT because the almanac values are given for GMT. All right, so let's go into the almanac then and have a look. Let's do nautical twilight first, and then we can do civil twilight after that. Okay, now in the almanac, let's get to the almanac again. Right, so this is the right-hand page. We're obviously looking for this page. So October 21st, it's the first one here. We are looking for Aries, which is the datum basically for our star, for most of our star sites. We're looking at 2100 and 2200. So first at 2100, we have a tabulated GHA for Aries, 2100 at 345 degrees, 45.6 minutes. So 345, 45.6. And this is, of course, the left-hand column, eh? So for nautical twilight, which was at 2149, we have 345, 45.6. And then the 2200 one on the right, the 2200, we had 048.1. 048.1. Everybody see that? Everyone happy with that?
Yes, sir.
Okay. So tabulated GHA for Aries, 345, 45.6, and 048.1. That, of course, will be subtracted, eh? So remember that formula that I just had down here? We need to subtract the GHA. That's very important. This will always be subtract. And you'll see in this case, the value is actually larger. That's fine. Okay, so that's the tabulated GHA. But now we know that in order to find an SHA, we're not only interested in the tabulated GHA, we want the complete GHA. So this value that we see over here, the 345, 45.6, is at exactly 2100. But we're not interested in 2100, we're interested in 2149, isn't it? So that means we need to take the 49 minutes into account as well. Because this time that we eventually come down to 2149, the time, that is the SHA that we wanted for that exact time, 2149. So that means we need to go to the yellow pages, and we also need to include over here, from the yellow pages, we need to include the interval or the increment at 49 minutes for this one, 49 minutes, and for this one at 20 minutes. Everyone happy with that? Are you following?
Yes, sir.
Okay.
Yes.
Right. So
Yes.
in the almanac, we're going to go and look at 49 minutes. And we're going to look at 20 minutes. Okay. And then those two values are going to come in here, and then we can carry on from there. So we want 49 and we want 20. Then go down to the yellow pages here, 12. 42, 45, 48, 49. Yes, 49. Okay, so for 49 minutes. So this is obviously rounded to the nearest minute, so we don't need to worry about the seconds. So 49 minutes, 0 seconds. So the very top value that is the one that we're interested in. And obviously we're dealing with stars. People, this is very important. We're dealing with stars, so don't take this value because we're so used to just going to the almanac and take the first one that you see here for sun planets. Then remember, in this case, we're looking at the stars. We're dealing with the stars, so we need to look at Aries. That's very important. So we're interested in the value for Aries, which is 1217. So at 49 minutes, the increment, so the HA increment for Aries at 49 minutes is 12 degrees and 17 minutes. 12 degrees, 17 minutes. You can write that down in the meantime if you haven't done that yet. That's 12 degrees, 17. And we can go back to 20 minutes. With 20 minutes, we're going to do the same thing. So 20 minutes, 0 seconds. We are interested in Aries, and that gives us a value of 5 degrees. I should probably zoom in a little. 5 degrees, 00.8 minutes. So we have 1217 and 500.8. Okay, so that needs to go in here as well. So in the first one we have 12 degrees 17 minutes, and then in the next one we have 5 degrees 00.8 minutes. So now you can subtract that from the 263, and that should give you a value over here. Right, so you subtract that, then for nautical, you're going to get 265, 21.4. 265, 21.4. And for civil, we're going to get 257, 35.1. Is that correct? You agree?
Yes, sir.
Okay. Right. So this means that at, like I said earlier, at 3:49 in the morning or at 21:49, either one, it doesn't really matter, I guess. So at 3:49, at the time of nautical twilight, any star that is at Upper Meridian Passage at that time, at that exact time, 3:49, that star's SHA will be 265, 21.4. And then the later time that we're using, the 4:20, So any star that is at Upper Meridian Passage at 420 will have an SHA of 257.35.1. Okay, so between 265.21.4 and 257.35.1. This means that in between these two times, there is a range of, if you take these two and you subtract them, that gives you a range of 7 degrees, 746.3. So we have a range between these two times, so between nautical and civil, the time that we are looking at, we have a range of 7 degrees, 46.3 minutes. So any star that falls within this range will be at Upper Meridian Passage in between these two times. Okay, so once you've written this down, everyone happy with these calculations? Anybody got something else?
Nope.
Sir, can you show me where you, what did you subtract what from what to get 265? I'm confused.
265. Okay,
Yes, please, sir.
I started at 263. Then I subtracted 345, 45.6. And then I also subtracted 1217. And you're going to get a value of like minus 90 something or minus 80 something. Minus 90 something, I guess. Minus 94. What's this?
38.6.
Yeah, 94, 38.6. Negative.
Yes.
So you take that value, you subtract this, and you subtract this, then you're going to get a negative 94. Now, as you obviously any angle that you have that's negative, all you got to do with that is you just add 360 to it. Yeah, so you add 360 to it, that's going to give you back into the positive range, and that's going to get you 265.21.4.
Okay, I got it. Thank
All right.
you.
Then on the right, this one was straightforward. It's just minus 0, minus 5, and that just got you to the 257. Okay, anybody else have queries on anything in this table? Anything here that's unclear?
Could you please show again how do we come out with the range of
Oh, I got the
results?
range. Okay, so the range, the SHA range. So for this one, I just took saying if this is the first one and this is the second one, then that means the range must be between these two. So I took that one, I subtracted this, and I got to that. So the range is basically between this and this.
Got a question.
Yes?
Yes, the tabulated GHA of errors.
Yes.
Why why do we subtract the UMP star from that? Why do we subtract that value from the UMP star?
You subtract the GHA. You subtract the GHA because LHA is equal to GHA plus SHA.
Oh yes.
So remember when we are doing a Marx and Tilley, right? And you're starting at your GHA and you're working all the way down to get to an LHA for a star, you always add SHA, isn't it? It's always a plus.
Yes.
So that means if you want to find SHA, so you're changing the subject of the formula. That's why I put the formula down here earlier. You're changing the subject of the formula to SHA. So that means if you've got SHA starting with LHA, you're working in the opposite direction. So now you don't add anymore. Now you got to subtract.
All right.
Okay. So this will always be a minus. You can write that down as a rule. When we're doing star calculations, so for tab GHA and HA Aries, this will always be negative. Working this way. All right, so it's always going to be minus. All right, so now that we have these parameters here for SHA, we know that the stars we are looking for, so a star that has an SHA anywhere between 257.35.1 and 265.21.4. Right, so I'm just going to put that in green maybe as well. So any star that has an SHA between those two values or in this range, any star there, we will be looking at. So if we go to the almanac, So we go back to the almanac. Okay, so October 21st, here we are, back to this one. So we're going to go to this table on the right here that gives us all the info for the stars, SHA, and the declination. Now, in this almanac, in the 2020 almanac, you will see that the information is actually recorded in such a way that it starts, it's not alphabetical. So in the 79 almanac, the stars are named or they're listed alphabetically by name. In this case, you will see that they're actually arranged by SHA. So they're starting at the maximum SHA, 357, and it goes all the way down to 13. Okay, so it's new. In this case, it's sorted by the number, by the SHA, which makes it easier for what we're looking for because we're actually looking for SHA, isn't it? It makes it a little easier to use in this case than the 79 almanac. So what are those SHAs we're looking for?
$265.
265 and 257, eh?
Yes.
So we simply start at the
Yes.
top and we work all the way down. You're saying, okay, so 265 and 257. Now, so we've got 270, which is outside our parameter. Then we have 263. Does that fall in our parameter?
Yes, yes.
Yes, it does, because we've got 257 up to 265, isn't it? So that means
Yes.
that the 263 falls inside our range, and the 258 also falls inside our range, whereas the 255 is just out, and the 270 is just out. So that means we've got 2 stars over here. So 2 stars that fall inside our range of 265 down to 257. Okay, so both of them are applicable. So that means you can take this down. So you can take this down. So the first star is Canopus, or Canopus, or whatever you want to call it. So that's the first one. It's got an SHA of 263.53.7. And then this value on the right here, which is a negative, this is a declination. Okay, so you can take this down as well. So we have a declination for the star, for Canopus, Canopus, whatever, of minus 52 degrees, 42.1. And if you see negative, what does that mean?
South.
South. Okay, so for these declinations, okay, so the value on the right there is a declination. So for these declinations, if it's negative, it means south. If it's positive, it means north.
Sorry, sir.
Yes.
For the AM, not calculated for
Yes.
the first value, 265.
Yeah.
Isn't that that value greater than the 263 that we took for Canopus?
Yes. Yes, it is.
So
It should be greater because remember, we have at AM twilight, so at AM twilight we have 265, or AM nautical twilight was 265, and then AM civil twilight was 257. So that means that we've gone from 265, if I can put, maybe if you can
oh yeah,
put the 265 in between there somewhere. So somewhere between the 265, which is there, and the 257, which is down here, is what we're looking for. So that means that because that value is going downwards, you see, so that means this must also be less than. Does that make sense?
Yes, got it.
All right. It could also have been the other way around. It could also have been that your first one was a smaller value and your second time was a larger value, and it would have gone upwards. But in most cases, it will be going down like this. All right. Now, That's the two values that we've got. I take it everyone's taken that down, so I'm going to take this away. I'm going to switch back. Yes, I see in the chat someone's talking about sound. So somewhere, actually, I'm just going to mute everyone that's not muted, because there's like some construction going on in the background there somewhere. All right, so let's go back to the Excel sheet. Right, now, excuse me, from the table, from the almanac, this is basically what we got. So we got our first star, which is cannabis, at 263.53.7 SHA. And again, to come back to that question you had, so it's somewhere between 265 and 257. Must be between those two. So 263.53.7, and the declination of, because it was negative, is 52.42.1. And then our second star, Sirius, is 258 degrees, 29.0. And 16 degrees, 44.3 south. So everyone happy with this value? With these values? Any uncertainty on where that came from?
No, all okay.
Everyone happy? Okay. Right. By the way, as an interesting fact, does this name ring a bell to any of you? Sirius? Star Sirius?
Yes, brightest star in the sky.
Brightest star in the sky. Okay, good. Yeah, in case you didn't know, this is actually the brightest star visible from Earth. So in our galaxy, it's the brightest one. If you go in the almanac and you look at the magnitudes, you'll see that one's got the brightest value, or the lowest value actually. Right, so now that we know this, that means we can now look at the times, okay, at an exact time. And now you really gotta keep up with what I'm doing, because again, with this time increment, just like we've done before, we're gonna have to play around with some values, and basically we're gonna do interpolation again, just like we did with the sun and with Venus as well. Okay, now the first thing we got to do is we're going to say the GMT. So we're going to start off with the GMT for Upper Meridian Passage at nautical and civil twilight. Now, very important, when we start this off, we are not going to start at 2100 like we did before, because our starting time here, remember when we did this calculation, to get to the SHA, we calculated the SHA not at a time of 2100, but we actually included the increment already. So we've corrected it up to 2149. Do you agree? So this value here, 265.21.4, is at 2149, isn't it? Not at 2100.
Yes.
Right. So that means that this time over here isn't going to be 2100, it's going to be 2149. Okay, guys, so just I'm going to go through that again. When we are dealing with this, so you'll note here that it says GMT. It's not a tabulated time like we did in the past. We said tabulated time from the almanac, which was fixed to 1 hour. In this case, we're not doing that. We're saying it's the GMT for Upper Meridian Passage, for nautical, and then for civil. Right? So the tabulated time, Actually, we can even take civil out because we're not even going to use that. We're just going to use nautical as the base. So for nautical, that time is 21:49. And we're going to take that exact 21:49 and bring it down here. Okay, and same over here. In both cases, we're going to use the same time. That's our starting time is 21:49. And we use this because we know that the range, the time that we're looking at, there's a 31-minute interval from 21:49 up to 22:20. So our base time, our starting time is 21:49. And that includes already the increments. That's why we did the increments up here. So now that's already included by the time we got to this. Okay, so that's very important. So we're going to start off is back to the 21st again because we're back to GMT. So it's on the 21st of October, and the time now is not 2100 as a starting time, it's going to be 21:49. Everyone happy with that?
Yes, sir. I'm happy.
Right, okay. Now, the next part is where it gets a little challenging. Okay, so I'm going to do this. I'm going to use this table again since we've already got this constructed. So we're going to have to interpolate again with the time in this case. So we're going to interpolate again. Now, we have a total range. We're going to have to look at SHAs now, and then we're going to use that to then calculate the time increment. Okay. Now it's very important. So remember, we said that at this time, 21:49, at 21:49, the SHA at Upper Meridian Passage is 265.21.4. So these two basically go together. Maybe I should just highlight that in a different color as well, or maybe put the writing in a different color. Those two go together. So this time is that SHA, and the same for this one. Does everyone see that? So this SHA 265.21.4 is Upper Meridian Passage at 21:49. So that's our starting time. Then the next one, the 257.35.1, just trying to find a color that'll actually work. That one, what time is that linked to? That's linked to the 22:20, isn't it? Does everyone see that?
Yes.
So this one's
Yes,
at 21:49, and this one is at 22:20. So that means if we are looking at this year, so we have 21:49, and our next time is 22:20. Okay, and for the other one, it's going to be the same. So trying to find the time increment.
So can I ask a question?
Yes.
How can you say that the two GMTs for the two stars are related to those times? Because didn't we just calculate for nautical and civil twilight? So how can we just say that the one is related to the other one?
Because remember, at this stage, this value, the 265, right? That 265 isn't any one of these stars. The 265 is actually the SHA for any star at exactly the same time as this nautical twilight. So this SHA is basically it links to this time in the sense that at this time, at exactly 21:49, any star that is at Upper Meridian Passage at exactly this time will have an SHA of 265. So this SHA of 265 basically is the limit, or the starting value for what we're trying to find, our range, because that is the SHA at this time.
So basically you're just using the closest value to the closest star, and then you're going to interpolate one from the back and one forwards. Is that right?
We'll actually interpolate both of them from the same baseline. So we'll interpolate both of them from 265. You could do it either way, it doesn't matter. But in our case, we'll just take both from 265, because then this means this is the same time. But if you want to go from this one forward and from that one back, you could.
Okay.
Okay.
I'll just keep watching.
Right. Okay. So guys, this part here is very important. So again, with the interpolation, like I said earlier, if you're not sure, you need to go and practice this. By the way, do you have a class after this?
Yes, we do.
Yes.
We've got another class at 10 past, eh?
Yes.
Okay.
Yeah.
Right. That means we need to, we'll probably finish up the time here, and then when we're done with the time, we'll have to come back to this. So again, we're not getting to this, but that's fine. I'll just run you through that anyway. Okay, so we've got from 2149 to 2230. Right, now the starting SHA here is 265.21.4. We're going up to 257.35. So the range is this, the 746.3. Okay, that's our total range. Okay, so the range, I'll just put that in there. So the total range from there to there is 746.3, right? Now, that is for a total time of 31 minutes. So 31 minutes from there to there. So in 31 minutes, the SHA changes by 7 degrees 46.3. Does everyone see that? So in a total of 31 minutes, we are covering the total range. Right, now, for our 2 stars, we know actually now what the exact SHA is. So that means if we take this exact SHA and we check the difference between this SHA and our starting SHA. So we start at the 265 and we go towards the SHA for Canopus. What are we going to find as a value? So from there to our SHA for Canopus, we get 1 degree, 27.7 minutes. Is that correct?
That's correct.
Okay. So that means that from the time, so if this is the time of 2149, then obviously we're trying to find this time, the time for Upper Meridian Passage Canopus. So we're trying to find this one. So the difference from there to there is 1 degree 27.7, and that 127.7 is out of a maximum of 746.3, isn't it? Which means again we have a fraction. Does everyone see that? So we get 127.7. So from there to there, we have 127.7 out of a maximum of 746.3. So that means that that is also going to give us a fraction. So it's going to be a fraction of 0.188. That first one. Actually, let me put that down here. So we have a change. We have a change of 1 degree, 27.7 minutes, out of a maximum of 7 degrees, 46.3 minutes. If you divide that, you're going to get a fraction of 0.18808. You guys agree with that?
Yes.
Okay,
Yes.
Everyone's happy with that? You're all happy with how I got the 127.7?
Yeah, we
From
good.
there to there, eh? So from 265 to our SHA. Out of a maximum of that, we get a fraction of 0.18. Now this 0.18, we know that the total time, or the total change in time, is 31. So that means that if this is the fraction of the SHA change, then the same fraction will also be applicable to the time change, isn't it? So for 31 minutes, so we take this 0.18, we multiply that by 31, and you're going to get 5.83 minutes. So if you go blue function HMS, with that 5.83, you're going to get 5 minutes,
49.
5 minutes, 49, and then 49 again. Okay, so 5 minutes, 49. So 5:49, 49, and that's that second 49. Does that round up or down?
Down.
Up.
Rounds
Down.
up, doesn't it?
Yes.
It'll round up because remember, as soon as you switch to HMS, then your decimal functions are out of 60. They're no longer out of 100. So that rounds up. So 49, 49, which goes up. Because if that had been hours, it would have been 5 hours, 49 minutes, 49 seconds, isn't it? So that 49 would round up. Okay, so that becomes 5:50. So 5 minutes and 50 seconds, is that correct?
Yes.
Okay, so that means that the time interval is 5 minutes and 50 seconds. So that's 000550, which is added to that. And that's going to give you a time of 21:54:50. Which will still be on the 21st. Okay, so let's have a look at the second one. So we're going to do the exact same thing. So if you're not sure what I did, it's fine. We're going to do the exact same thing here. Okay, same principle. So we're starting at 21:49. Starting at 21:49, which is again the 265. So we're saying from our starting SHA of 265.21.4 to the SHA of Sirius in this case. Okay, so from the starting SHA to the SHA of Sirius, what's the difference there? Okay, so we're going to calculate that difference. We take 265.21.4 and then we subtract the 258. That's going to give us a value of 6 degrees, 52.4. Everyone happy with that?
Yes.
So from there to the SHA of Sirius gives us 652.4. And again, it's out of a maximum, the same value, 746.3. So you take that value and you go 746.3 and you divide that. That's going to give you a fraction of 0.89014. Now that same fraction again, you'll take the fraction, you'll multiply it by the change in time, the total change in time, which is 31 minutes. And what does that give you? So what do you get here as a change for your time increment?
0.
Sorry? Anyone got a value for me here?
-27 minutes 25.
27.25.
That's correct. Yes, 27.25.
Do you guys agree?
Yes.
Okay. Yes. So you add all of that up. That's going to give you 22.16.25. And then, of course, if you apply your zone difference of +6, just like we did there, that's going to take you back over to the 22nd. And then you'll have a time of 3:50, 3:54.50, and 4:16.25.
Sorry, sir, how did you get 0.890414?
Okay, I'll tell you just now.
Yeah, I'm not getting this value.
Yeah, I'm getting 0.88441.
84, yeah.
That's correct.
Yeah.
Okay, it could be that I made a mistake there. Let me just check that again. So we have 6.5224 and 7.4618 divide 0.88441.
Yes.
Yes, that's correct. So it's just a button bashing mistake on my side.
Okay.
Right, but this is still correct. So it's 27.25. Carry that through. It's going to give you that time, and I think it's just gone 10 o'clock. So that basically concludes our time. So what I want you guys to do, I'm going to explain something quickly. I'm just going to take a minute, and then we can call this for today. So you would have noticed yesterday there was a test going online on Blackboard. Did you guys see that?
Yes, sir, we saw.
You saw it. Okay. Now that test, the test that went online yesterday is for this exercise, this exact exercise that we just did. So that means the test is live. I made it live this morning. So if you go onto Blackboard, you can go and have a go at the test. It doesn't count for marks, it's just a practice. So it's a practice test, again, just to get you used to working with Blackboard. And you will see that it's this exact exercise. So what I would suggest is maybe somewhere this afternoon when you're done with everything else and you've taken a bit of a break, you can start this exercise again, have a go, run through the whole thing. You now have the answers. You can have a run through the whole thing and then do it as a test on Blackboard and just follow the instructions. The instructions are very clear with regards to decimals and how you need to put in the values and all of that. You can put in all of these and you can basically do the whole test online on this exercise for which you already have the answers. Okay, so that's the test that went online yesterday. I'm actually surprised no one asked about it. Now, the last part here, the last thing that we need to do is predict sextant height. So I'm just going to very quickly take you through this. I'm not going to put in values because we don't have time and I don't want to steal your time from your next period. Okay, now remember I told you guys you need to draw this line. You need to get used to making a diagram like this and basically figure out ZX, how ZX relates to everything else. Remember we went through this last week. Okay, so I'm going to put this on Blackboard as well, this working of this example, by the way. So when we want to predict a sextant height, we need to start with HO and work everything in reverse. How do we find HO? We find HO when we know that what ZX is, because HO is complementary to ZX, remember?
Yeah.
You'd remember this from S1. Okay, so HO is complementary, so 90 degrees minus ZX is HO. How do we get ZX? We get ZX by doing this diagram. We take our latitude. This is a DR latitude, of course, where we expect to be. So we say that ZX, in this case, ZX1 for Canopus, ZX1, in this case, ZX1 is Canopus and ZX2 is Aries. So ZX1 is QX declination minus DR latitude. Okay, and you get that from this. That's going to give you a value for ZX, right? Which in this case is 20. Then you do the same thing for the second one. You say latitude minus declination. Okay, latitude minus declination. That's going to give you that value. And then from here, you basically just run down all the way to HS. So I will come back to this next week. But in the meantime, now that you know what to do, you're welcome to go and try it on your own. Okay. I will put it on Blackboard as well with the answer. I just want to just make this black. So I'll put all of this on Blackboard today. Then you can have a look at this. You can have a go at that test. And then I think that concludes our session. Okay, so there was a lot of new stuff today that you may not have seen before. So go and practice it, sit with it. And remember, I told you guys last week, if you need to contact me, people, I know this is a different setup to what we normally have. And typically I wouldn't encourage people to contact me via or on the cell phone at least. But in this case, we know it's extraordinary circumstances. So if you really need to get a hold of me, then get a hold of me. I did tell you this last week, eh? If you need to contact me, you can contact me. I'm not gonna be upset if you contact me. Obviously, if you try and contact me at 2 o'clock in the morning, you're not gonna get anywhere. But don't hesitate, please. If you need to get a hold of me, do that. And if you need to get my number from someone, then get my number from someone. And obviously, this goes without saying, but if I say this, then automatically, if someone does ask for my contact number, from those of you that do have it, it's fine, you can share it. But obviously, don't abuse it, guys. Right, so with that being said, I'm going to stop. You guys can take a quick break before your next class. And then I will see you again on Tuesday.
So what is the best time to get hold on you?
You can get hold of me anytime during the day, because I'm at home, so it's not, you can get hold of me anytime. It's just that like 2 o'clock in the morning, I'm not going to respond. but
Okay.
I'm not too worried about what time. So you can send me a message during typical office hours, I guess, would be the best between 8 and let's say 4 or 5 in the afternoon. Okay.
And so when you're gonna upload this exercise?
I'm gonna upload it right now.
Blackboard.
I'm gonna put it up now. Okay.
Great.
All right, guys.
Thanks.
So enjoy the rest of the day. Have a good weekend. I will see you next week, Tuesday.
Okay, thanks.
Okay.
Thank you.
So can I please ask questions?
Yes.
But it's okay. I don't mind missing Nava because I just have something I want to ask.
Yes, that's fine.
So the first one is, it's just back to this calculation you did.
Yeah.
I don't know why I can't get the